Hey guys, it's your boy.
Reed! No, we are not starting off another video like this.
Radiation Reed, come back at
You
ya
promised.
with another one of
Reed!
Nodgevitz. Fine.
I'm Gabriel.
And I'm Reed.
In the world today, there's a lot of talk about radiation. We often hear phrases like half-life and radiation poisoning. For something that we clearly give a lot of thought to, it's alarming that most people don't understand the science behind it. If we're going to talk about something so much, we should actually know what we're talking about.
Are you thinking what I'm thinking?
Unfortunately, I think I am.
Time to transmutate.
It's Gamma Game.
And Radiation Reed.
With that unpleasant business out of the way, let's get to the basic science of radioactivity.
Yeah.
Stability is the dream of every atom. When an atom is unstable, it will do whatever it takes to become stable. It does this by emitting different types of radiation.
If an atom is stable, it will follow different rules depending on which group it is.
In the first group, all elements under atomic number 20. An element is only stable if it has the same number of protons and neutrons. Let's take carbon as an example. Carbon has 6 protons with an atomic number of 6. Because its atomic number is below 20, we know that there must be the same number of protons and neutrons in the nucleus for the atom to be stable.
Carbon-12, which has 12 protons and neutrons combined, is sadly not radioactive, with 6 protons and 6 neutrons. The number is balanced so the atom is stable. But there's a more exciting example, carbon-14, radioisotope of carbon. Radioisotope just means an isotope that is radioactive. Carbon-14 has 6 protons, but the mass number tells us that there are 14 protons and neutrons combined. So we subtract the 6 from 14, we know that there must be 8 neutrons. Any element under atomic number 20, like carbon, must have an equal number of protons and neutrons to be stable. So with 6 protons and 8 neutrons, carbon-14 is radioactive.
Nice job, Reed.
It's radioactive.
Nice job, radioactive Reed.
Thank you. In the second group, elements over atomic number 20, there must be more neutrons than protons in the nucleus for the atom to be stable.
Take iron 56, for example. Iron is atomic number 26, meaning it has 26 protons. If we subtract 26 from 56, we get 30, which is the number of neutrons. So iron 56 has 26 protons and 30 neutrons. There are more neutrons than protons, so iron, which is above atomic number 20, is stable and it's 30 neutrons.
One more group, and then we must talk about radiation.
The more neutrons than protons rule works up to a certain point. But once you get above atomic number 82, all elements are radioactive.
They stay that way until they are able to lose enough protons to be below atomic number 82. They do this through radiation.
An unstable atom has a few different tools at its disposal for getting rid of the extra energy and matter that's making it unstable in deep space.
Those tools are different types of radiation. These types of radiation are gamma, alpha, and beta.
Gamma radiation is pure energy, and thus is very dangerous. Gamma rays can destroy cells and are difficult to block, demanding materials like lead or concrete.
Gamma rays are the highest energy waves of the electromagnetic spectrum, the same spectrum that visible light and radio waves are part of.
Gamma radiation can be represented by the symbol on my shirt, the Greek letter gamma.
Because gamma radiation is pure energy, there are no units of gamma radiation. Instead, gamma radiation is a symbol used in all cases.
Gamma blast! No, just a demonstration.
I should never let you be gamma, Dave. Now for alpha radiation. Alpha radiation is when an alpha particle consisting of 2 protons and 2 neutrons is released from the starting atom's nucleus.
This particle is identical to the nucleus of a helium atom. In fact, alpha particles can be written as the isotope notation of helium, with a mass number of 4 and an atomic number of 2. can also be written as the Greek letter alpha.
Now time for a visual demonstration. So if you pretend I'm an unstable atom, I eject an alpha particle.
Moving on. The final type of radiation is beta. Now beta is a little more complex than the other types of radiation, because there are actually 3 types of beta radiation, instead of just one. The first type of beta radiation is
Beta minus radiation.
back already, huh?
Yep. In beta minus radiation, a neutron becomes a proton and an electron, which flies away.
This typically happens to atoms with too many neutrons and not enough protons to be stable. In beta minus radiation, neutrons are lost while protons are gained. Let's take me as an example. Imagine that I'm a neutron. Most of my body has a positive charge, but a small portion of me has a negative charge. My glasses, for example. Now, in beta minus emission, an electron flies away from the body of the neutron, leaving only a proton, like this. The second type of beta radiation is beta positive, which is exactly what it sounds like. The opposite of beta minus radiation. Atoms that have too many protons and too few neutrons to be stable might undergo beta radiation, which adds neutrons at the expense of protons.
In beta positive radiation, a proton turns into a neutron and ejects a positron. A positron is just a positive charged electron and it carries a positive charge away from the proton, turning it into a neutron with a neutral charge.
The final type of beta radiation is electron capture. Electron capture occurs when a passing electron attaches to a proton in the nucleus of an unstable atom. Their positive and negative charges cancel out, and the proton turns into a neutron. This has the same end result as beta positive, a proton transforming into a neutron.
A cool fact about beta positive radiation is that when a positron meets with an electron in another atom, they will destroy each other and a gamma ray will be released. Beta positive and negative radiation can be written using the Greek letter beta, either with a plus or minus sign. Electron capture has no symbol.
Beta negative and electron capture can emit dangerous gamma rays, as can a positron when it meets an electron. The electrons and positrons themselves are not particularly dangerous, blockable with a sheet of aluminum foil.
Yeah.
So now you know when an atom is stable, what types of radiation unstable atoms can use to become stable, and how dangerous different types of radiation are.
We also talked about how radiation is written, and we touched on radioactive decay equations.
Now when we're talking about nuclear bombs or power plants, you'll actually know what you're talking about from a scientific perspective.
Thanks for watching.
Or at least suffering through it to the end.
This has been Radioactive Reed
And Gamma Gabe, we're out.
You're supposed to get it. Come on.
What do you mean get it? It's a basket. The basket doesn't move.
Yeah, it moves in my mind.
Stop throwing pumpkins at me. Disgusting. You disgusting rat.
Ready? We got you. We got you.
Stop. I mean, just stop. Okay, can you actually help clean up though?
Okay.